Dear student, today we start chapter 6, neighborhood processing. And this chapter is a simple chapter, it's not complicated, and it's very interesting chapter. So we start by enhancement. What's mean image enhancement? So the basic goal of image enhancement is to process the image to be viewed more clearly than original, which means that if the image is not clear, if there is a noise, we denoise the image. If there is something to be cleared or to lighted on, to be more visually accepted or pleasing by the viewer, and to be more suitable than the original for the required purpose. Because the processing of image has different purpose. Sometimes you need to play on the colors. Sometimes you need to differentiate between two objects, background, foreground. So we need to make a binarization of the image. Or to create a binary image. Sometimes you need to extract feature from the image, for example, geometric forms. Sometimes we need to find occlusion, for example, in medical image, and so on. So every kind of image have a specific purpose. So the enhancement of a similar image is to enhance the parts that is required to be cleared and to be viewed, to be lighted up. So it's a subjective, which means subjective. It's difficult to evaluate the image enhancement. Why? Because if we have different images, we cannot say that the image 1 is better than image 2 or image 2 is better than image 1. It's a subjective purpose. Sometimes some people may find image 1 better than image 2, and some people find image 2 better than image 1. So there is a difficult criterion to quantify or to make a quality of this image. But if we have some criterion, for example, if we have some parameters, if this parameter is greater than the other one, we can say this image is better than the others. But in image processing, in general, we don't have a criterion to compare the image as equality. Of course, we have qualities as signal to noise and others, but in general, for the image, we don't have equality, so it's a subjective. And the performance depends on the specific domain of application. As we said, each domain of application has its specific requirements and has a different type of information that should be extracted. So in this chapter, we need to enhance the image via filtering. As an example of image filtering, removal of noise. If the image has noise, we need to delete this noise, remove this noise, or denoise the image. Sharpening of image edges. If we have an image and we need to find the edges or the border of the different components in the image, we may make soft focus. For example, blurring the image. If we have a blurring image, we need to reduce the blurring or make a blurring, and so on. And in general, the enhancement via filter, it's a special domain processing, which means that the filtering is applied on the pixels of the image, and these pixels are processed directly. So we apply our filtering on the pixels. So the value of pixel are changed according to a certain formula, and this formula is based on a specific filter. So filtering an image, it means that we change the value of pixels in a specific way. For example, I may find the pixel, every pixel is, for example, the average of the surrounding neighborhood, for example, or the PV value of pixel of the output image if the maximum of its neighborhood, and so on. And this filter can be classified as linear and nonlinear. So we have two types of filtering. And the value of target pixel after calculation of the output image is replaced by the new value. And this value depends on the pixels of a specific neighborhood. So we will define what's mean of neighborhood, and after that we define what's mean of linear filtering and non-linear filtering. So local neighborhood, it means that we determine the local area of influence and relevance, which means that if I have a pixel at the position ij, what are the neighborhood, or neighborhood it means voisinage, يعني الجيران اللي حواليها, that form the local area, يعني the number of pixels that can affect these pixels, يعني جيران البيكسل اللي عم نحكي عنها اللي ممكن يأثروا عليها. This kind of pixels, this number of pixels, it's called the local neighborhood. We may have, for example, 3 pixels around the target pixels. ممكن اخذ البيكسل اللي عم دور عليها، اخذ 3 بيكسلز على اليمين وعلى الشمال ومن فوق ومن تحت، ممكن اخذ 5 بيكسل، ممكن اخذ 7 pixels, ممكن اخذ 9 pixels. So it depends on the size of the window. النيبرهود بنسميه window. So we define the pixel that are connected together, which is these pixels that form the window, and this window will be centered by the target pixel. And after that, our objective is to determine if pixels have the same feature or no. الهدف اني اذا اخذ هالبيكسل وشوف جيراننا اذا هالبيكسل متناسبه مع الجيران تبعها ولا لا. اذا مش متناسبه نطبق الفلتر لحتى تصير متناسبه. So this is the way of filtering the image. So we have 2 types of connectivity. The for connectivity, where we take only the north, south, east and west. يعني باخد بس اللي فوق واللي تحت وعلى يمين وعلى شمال. This is the for connectivity. The 8 connectivity, which is the most used type of neighbors, باخد الwindows, all these 9 pixels. This 9 pixel consists the neighborhood of the pixel ij. So the pixel ij is calculated based on the value of the neighborhood. Let's say we have 8 neighborhood. If we extract the middle, which is ij. So for example, one of the filters, I can replace ij. Every pixel ij is replaced by the average of its surrounding pixels. يعني باخذ هذه النقطة الجديدة اي جي بالصورة الجديدة after filtering، هي الافريج المعين تبع البيكسلز اللي حواليها. هذا بنسميه for example median filter. طيب ليش باخذ انا median filters؟ because some noise، انا اذا عندي noise ممكن هالنويز يعلي الفاليو، ممكن هالنويز يوطي الفاليوز، بس اخذ الافريج ترجع الفاليوز لحالتها الطبيعية. So this is a kind of pixels of filtering. So we'll talk about this into the next slides. So the majority of image processing technique, as we said, use 8 connectivity, and the neighborhood is generally squared size n by n times s, n times n. أحيانا بيكون rectangular n times m. So ممكن 5 times 5, ممكن 5 times 7, 7 times 9, and so on. So pixel of the local region. So we have the middle pixel, which is the local pixel location indexed ij. In general, it's center of the window, and the neighborhood as indexed I plus minus k and j plus minus k, where k is in general n over 2. So this is the way we filter, and which means that this is a pixel ij, this is I plus 1, I minus 1, this is j plus 1, j minus 1, this is I plus 1, I plus 1, j minus 1, this is I plus 1, j plus 1, and so on. So for that we have adding a plus minus k and j plus minus k, and since I is the middle and the size of window n, so k is an offset for value n over 2. And the special filter operation, how we apply this special filter operation, we apply this on a series of local neighborhood operations using sliding window principle, which means that we take a window, for example, of size 5.5. We apply this on the filter, then we slide the window, بنزيحه للwindow 1 pixels, then we apply again the filter, then we slide the window by 1 pixels, we apply the filter, and so on. بس يخلص in row بننزل 1 pixels or 1 row نزول ونرجع we apply the filters again and again. So we obtain a series of sliding windows, and every time we apply the filter in order to calculate the new value of the centered pixels of the window. So we have this formula B equal NL filter, which is a neighbor local filter, A, MN, and function. This is a perform sliding window operation. A is the image, MN are the size of the window, which is in general can be squared and can be rectangular, as we said, and F function, which is the function that to be applied. So what is the function to be applied? For example, it's average, function, minimum, maximum, median, and so on. So the function define the function handled, fx can be maximum, minimum, mean, median. These functions are MATLAB functions, so we can use that directly. And add x in order to define the variable x, that this function has a variable x. And of course, if we have any function, you need to use the unsigned integer a of mean x, because after calculating the mean or the if we calculate, for example, mean and max, there is no problem. But if you calculate the mean, which is the summation over the number, so the value will be double. So in order to obtain a value that is unsigned integer between 0 and 255, so we need to apply unsigned integer 8 to it. يعني احنا لما نكون عاملين نجمع الماكسيموم للبيكسلز ما عندنا مشكله، المينيموم ما عندنا مشكله، المين هي جمعهم على عددهم بيطلع الرقم في فواصل، بينما الفاليو اوف ذا كولرز خاصه عم نحكي جراي سكيل لازم تكون unsigned integer والقيمه تبعها between 0 and 255. ففور ذات بعد ما احسب المين بدي اعمل unsigned integer 8، هو بيعمل لي transformation of the double values into unsigned integer values which be that correspond to one of the 256 colors. So this is imread camera man.div. This is a maximum function at x maximum, and this is a NL filters A33, and this is a function. So we can write directly at x maximum here. So we can directly write it here. And after that, we display the image. So this is the value of the maximum. So as you say here, we have a white. شايفين هون this is a block of white, which mean that عندي هون نقطة بيضاء بالغلط. Maybe by artifacts or like this, نقطة بالغلط بالبيكسل. كل ما اخذ جيران اللي حواليها وفيها هاي النقطة البيضاء رح تعطي الماكسيموم للبيكسل هي بيضاء. So for that, when عندي نقطة بيضاء رح يطلع حوالي block of white. So this is a block of white here, block of white, and so on, because we take the maximum. And also, where we have a white points, all the neighborhood will be white. يعني كل نقطة هي الماكسيموم بحد ذاتها 255. كل neighborhood of size 3 by 3 يعني رح يطلع عندي أنا 3 by 3 اللي contain the pixels رح يكونوا عندهم كلهم بيض. If we take the we increase the size here 3 by 3 يعني عندي شباك إذا عندي 1 point بيضاء رح يطلع عندي شباك of size is 3 by 3. But if this I increase the size of window 7 7 رح يطلع عندي the block by 7 7. 11 11 رح تصير 11 by 11, and you can see that the size of the black is reduced. شايفين السايز of the coat لأنه every time the size of window increases, so the pixel here اللي كانت سوداء حواليها في أبيض الماكسيموم رح يطلع أبيض, and so on. So of course here the quality of these two images is not good. Also, rather than take the maximum, we can take minimum, we can take the median. And you know which is the median. The median with the if you have, for example, a window of 3 by 3 معناتها عندي 9 values. So we order the values from the minimum to the maximum وبياخد النصان اللي هو رقمه 5 بالايكويشن. So this is the maximum for the same window 3 by 3. Minimum, لاحظوا المينيموم صار الماجوريتي black because every point عم بياخد المينيموم تبعها, so البلاك رح يكون هو الدومينانت. Here we have the median. لاحظوا هون بالميديان التموجات اللي كنا نشوفها هون ما عادت موجوده, صار تقريبا stable colors. الالوان خلفيه صار stable. Why? Because if we have any value يعني اذا عندي جيران مختلفين شوي بالارقام, لما اخذنا الميديان صاروا كلهم قراب لبعض, مشان هيك بنحس اكثر الالوان صارت ما عاد فيها التفاوت الخفيف بالالوان. الديجراديشن اوف colors ما عادت موجوده when we apply the median filter. So الفلتر kernel or kernel هو الويندوز اللي عم نحكي عنه احيانا بنسميه mask filters or convolution. And this is applied on special domain, as we said, where image is defined by the coordinates of its pixels. So we apply the kernel on the pixels. We have, if the filter is linear, معناتها target pixel have a linear combination of neighborhood pixels. So بس نحكي عن linear filters معناتها the relation between the neighborhood are a linear form. يعني مضروبين مثل summation مضروبين ب constant times the pixels. Then we make a summation. While using nonlinear, ممكن the value of pixel can be elevated square, cube, radical, log, and so on. So linear, it means just we multiply each pixel by a constant value, then we make a summation. This is what we call linear combination. While nonlinear, we can use any nonlinear function as that squared function, cube, power, local exponential, sine, and so on. And of course, we multiply by this weight, which weights are assigned to each neighborhood. So the filter procedure, we put the kernel so its center coincide with the target pixels, as we said. لما بنختار الويندو لازم يكون ال ij pixels هو at the center of this window. Now we calculate the weighted combination of neighborhood. نضرب كل pixels by its weight. Then we make the summation, and the obtained value is assigned to the ij pixels. And after that, we slide the kernel in order to cover all the pixels of interest in the original image. So this is the formula of the window. Every pixels I, xi, y plus j is multiplied by wij. Then we make a summation for the window. Of course, the window has it's a small matrix, so for that we have two summation. And x plus I, y plus j, and I and j from min to max, and also it's j from the value min to max. Fxa is the value of the new ij pixels, and wij is the weight, and ij correspond to the target pixels. Now we can linearize this function by taking all the pixels as a vectors, and for that we obtain a variant formula where fi is the value of the new pixels and wk is the weights, and just we take ik are the pixel of neighborhood, and k is linear, and it's running according to row and columns convolution convention. So يعني the difference between the formula above formula and the below formula is just rather than talk about window like this of data, rather than take this window and we make summation I and j from I minimum to j maximum, we can take these 9 values as a vector of data, بياخدوا كفector، وبالتالي بيصير بدل ما عندي index along I axis and j axis all along row and columns زي ما بنحكي matrix. So just we can take only one index which is k, and we take one weight which is wk rather than wi and j. So this is just the formula in order to simplify the formulation of the filter. So this is an example of how we make a filter. Let's say this is a kernel filter. We have these values. This is of the original image, and we take this value of the window W1, W2, W3, 4, 5, 6, 7, 8, 9, like 8, and all the others are -1. This is the kernel filter. هذا الفلتر عنده 8 at the center, which is for ij pixel, and for all the neighborhood the value -1. So if I applied this pixel here, so 10, 11, 8, 42, 46, 36, 38, and 40 will be multiplied by -1, and 35 will be multiplied by 8. And after calculating, we'll obtain 14. So at the new image, the output image, 35 is replaced by 14. And we slide the window again for the next values till cover all the image. يعني again we will slide this window by 1 pixels. يعني راح يصير عندي window جديد of size 3. So this is the new window. Okay, and after ending this part, we slide the window 1 degree. We slide the window 1 degree, one row or 1 pixel, and we apply again the window. So we apply again a new window. Now start here. This window is of type 3.3. So this is the window, 3 pixels. This is the window, and the centered value here is 37. Okay, so 37 now, how it's calculated, the new value of 37. We multiply 37 by 8, minus 32, minus 36, minus 40, minus 38, minus 89, minus 36, minus 41, because each one is multiplied by minus 1. And we make the summation, and the new value of 37 is calculated by the result of summation. Now we have a problem. What about the value at the borders, 40? We don't have any, we cannot create a pixel, a window of size 3 by 3, center it at the point 40, center it at the point 12, which is all the borders. يعني الحدود تبع الصورة البوردز اللي هو أول بيكسلز ما في يخلق له أنا ويندو شباك يكون السنترز هو البوردر بيكسل لا أقدر أحسب النيو فاليو. So what I have to do to find the new value of the pixels at the borders. So this is a problem that we'll talk about it later. So this is a step of the process. We define the kernel filter, what type of filter I have to do, the size, the formula to be applied. Then we slide the kernel filter over the image so that its center pixel coincide with each target pixel in the image for every I at j, and we slide horizontally and vertically. Then we multiply the pixel lying beneath the kernel by the corresponding weight as we made here, until then we make the summation of the total, and we replace each pixels by the new value, and we copy the identical value at the same location ij in the new filtered pixel, new filtered image. So in this way, we apply the kernel image and we apply that image. So region-based filter variant, we can apply the filter not in all the image, just in certain region of interest, which is another variant of kernel filter. And in this way, the filter is not applied in the entire image, just in the region of interest where we have problem or where we know to extract some filters. Another variant is an adaptive filter, is a sophisticated approach where filter is changed, which means that it depends on the distribution of the neighborhood pixels. Which means that in adaptive filter, in some parts, I may apply, for example, a filter of size 7.7, and in other part of the image, I applied a filter of size 5.5. In another part, I may apply a filter of size 3.3, for example. And this is an adaptive filter. For example, if I go to this image, if I want to apply a certain filter here, because there is the colors or there is no details, it's a background, there is no details on the image, I may apply a filter of higher size. For example, here I can apply a filter of size 9.9. Here on the grass, I may apply a filter of size 5.5, for example. But what I want to apply a filter on the foreground, for example, on the face of cameraman or on the camera itself or on the building, I cannot apply a higher filter because it may distort the details of the battlements of the building or of the face of the cameraman or the camera itself. So for that, in this place, I may apply a small filter size, for example, size 3 by 3 or 4 by 4 and so on. So this is what we call the adaptive filter. It concerns of changing the size of the filter in different part of the image according to the details on the image and according to the specification of each image. So this is what we call the adaptive filter. Now for the boundary, which is the problem that we talk about, the first approach, it leave unchanged the target pixels in boundary region. So, which means that when I apply the target filter here, when I apply the filter, the element here in the boundary 9, 12, 11, 12, 13, 13, 9, 13, 40, etc. will not be changed. So I leave it unchanged without changing it. But this will be an artifact, which means that I can see when I review the image that there is some artifact between the boundary and the processed image. يعني راح احس انه في مثل اختلاف بالصوره، بحس انه في مثل كانه انا عندي بحس انه كانه صورتين، صوره البوردرز هن منفصلين عن بعض. Why? Because when we apply So it's not good. مثل ما حكينا بحس انه عندي قطشه بالصوره، فما لي مصلحه اطبق خلي شو اسمه البوردرز like without like that unchanged, so which can make undesirable edges artifact. The other part is perform filter and adjust the filter operations. So the first approach, as we said, we let the pixels in the boundary region unchanged, which can cause or produce undesirable edge artifact. The second part is perform filtering and adjust the filter operations, which means that we can add a new borders, and after that we can apply border operations, which means that I add here a new border 12, 11 with the same value, 12, 11, 12, 13, 13. And like that, I can apply in a kernel filter. I can apply a kernel filter like this for the point, for example, for 11. For the value of 11, I can add this filter. This is a kernel of 3 by 3. So the 11 now will be at the center. And here the 3 points will be the same as in the border, 12, 11, 12, and then make the calculation. So this is how to apply this. This is one idea also. It can be applied. Another way is to fill the missing pixels by mirroring values over boundaries, which mean at the output pixels, I can add the values according to the output image, which means that after calculating the new values here, for example, let's say the new value of 8 is 25, and this is 24, so this is 25, this is 24, so this will be the mirror of this value. In this way, we don't have an artifact, but the best way is to copy the resulting value to the same location and make a crop the image by extracting the reduced image in size and removing pixel in the edge. After calculating the image, I remove the first row, first column, last row, and last column from the image. And in this way, I can reduce the image by two pixels and by row and 2 pixels by columns, but I ensure that all the pixels are processed. Of course, these 2 pixels will not affect the size of the image. For example, I have size of the image 700 pixels per 800 pixels. So if I reduce 2 pixels, this will not affect the image size. So this is a filter image kernel. We have after special, filter special. We have motion. We have, after applied the type of filter, we apply image filter A. This is the case, the type of filter. And here the time of bordering, for example, symmetric. Okay? And we apply the filter motion. So it's like we make emotion. This is, we like emotion. Like مثل ما نكون عم photograph a Ferrari, for example, at high speed, راح تطلع الصورة هيك because when we capture the pixels with a high speed, راح يطلع عندي هيك that a blurring image. So this is what we call the filtering by motion. So F special in general, we have average. We return the average filter of size, and this is the size of window. We can use disk, like I make a disk filter. So the neighborhood is a radius of disk of, and I put the radius. We may apply Gaussian, and of course, when you use Gaussian filter, we have to do the edge size and sigma. So as you know, Gaussian contains the size of filter and contains sigma, because each Gaussian filter has a sigma, which is constitute or determine the property or feature of the Gaussian filter. So you know Gaussian filter how it's, and sigma Gaussian filter هي شكل الجaussian اللي بتعرفوه هو على شكل جرس. بالطبع value of sigma هي بتصغر لي السايز تبع الجاوشن او بتكبره. Okay, we have Laplacian also. So also we give alpha for Laplacian, وشفنا طبعا الموشن من شوي. So this is, we take the image peppers, we apply average with window size 5.5, we apply disk with radius 4, we apply Gaussian of the window 5.5 with sigma 1.8, and every time we define F special and we apply image filter, and finally we apply Laplacian with alpha 0.7. So you can replace again, repeat again this function, and every time, for example, for average, increase or decrease the size of the window. For disk, increase or decrease the size of the radius. For Gaussian, you have two parameters. You can increase and decrease the size of the window, or increase, decrease the size of the sigma. Also, for Laplacian, you can decrease or increase the value of alpha. And for every time, see what is the influence or the affectation of alpha on the images. So this is the average. This is disk. You see some blurring. The image is light blurring. Gaussian filter. We see the quality is better. This is Laplacian, and Laplacian, it's a applied filter that determine the edges. You can see the edges, different edges. So it's not clear, very clear, but it's like it takes the edges between the different part of the peppers on the image. The nonlinear special filter. It's the same basic filter, but just the kernel mask slide over the image in the same way. Same mechanism, same for mechanism of sliding horizontally and vertically. What is the difference is that the formula is nonlinear. So for example, I take this formula and I take quadratic formula, for example. For every pixels, I have the summation square of these pixels and another weight times the value of pixel plus constant. So this way, for each pixel, I have to determine three weights. One for the constant, one that multiply the value of pixel, one that multiply the value of the pixels over a square. So the majority of nonlinear pixels are classified as statistical filter. So, and these filters are used for noise removal. So let's say we have two types of filter. So this is what we call the nonlinear filter. Now filtering for noise removal, why we apply filter? Some of the application is to remove the noise from the image. So some application require the removal of noise in order to increase the quality of the image. So also the filters that can be applied to remove noise are also divided into linear filter and nonlinear filter. And we have many kinds of noise that can be affected, so that can affect the images. So the most two important kind of noise are the most used are salt and pepper noise, which are called sometimes and of pixels, and we talked about it before. مثل ما قلنا قبل حكينا عن هذه السالت and pepper. بيكون عندي image and we have some pixels that have 255 value as white pixels, and some pixels have the value 0, which is black. So for that we call this salt and pepper. مثل كأني رشش ملح وقرفة سوداء على الصورة. So we have this may affect the the pixels and affect the pixels and may produce some distortion on the image. يعني ممكن تأذي الصورة. Another is to apply Gaussian noise. عندي جمع نوع من النويز يسموه Gaussian noise, and the function that can be applied to put noise on the image, image noise. So we have salt and pepper noise, the image salt and pepper D. D هي the density, which means that 0.05 يعني 5%, يعني 5% من البيكسلز راح تتغير الفاليوز تبعهم into 0 or 255, which means that white and black or salt and pepper. Gaussian white noise, also we applied Gaussian white noise. You have to define the mean of the Gaussian and the variance. And in this way, every pixels it will be changed according to a Gaussian function. Also, we have Poisson noise, image noise, I Poisson. You have speckle noise, which is multiplicative noise, which is a speckle. إذا حدا شايف ultrasound image, يعني صورة صوتية ultrasound image, حدا عم يخلف عم يشوف ولد أو for example عم يشوف إذا لنقول الكافيتي of the heart, يعني الكافيتي of the heart إذا عندنا مشكل if we have occlusion إذا مسكرين صمامات القلب, الأورطة and so on. So the image produced is speckle noise. We have local variance also, which means that we have the same Gaussian noise but with zero mean. Also, we apply local variance and we have to put the variance. So we have this kind of noise, but the two important are the pepper noise and Gaussian noise. So this is, we take the image 8 and we apply for each one a specific noise in order to study what are the effects of applying this specific noise. So we apply first salt and pepper with density 3%. We apply Gaussian with mean 0.25 and sigma 0.2. We apply Poisson noise. We assign or we apply speckle with density 0.04, and we apply local variance with this value of variance. So this is original. This is a salt and pepper. طبعا we increase the value for 3%. So for that, it's big density, salt and pepper. So this is a Gaussian noise because I take a big variance. So this is Poisson noise. This is speckle noise, as we said, similar to ultrasound. This is a local variance noise. This is what we call additive noise. So we add noise to the image. Now we need to apply filters in order to remove the noise. So I stop here and I continue the next video in order to not have a big video. And we talk about the filters, how to remove this kind of noise.